Okay, yeah, let's get started now. First, thanks a lot for the opportunity to speak here in this seminar. And yeah, this is work motivated by motivic philosophies like the Tannakian philosophy for the category of mixed motives over a field with rational coefficients. And up to now, we don't know that this is an abelian category, so we would look for a T structure on the so-called triangulated category of mixed motives, which exists. But what we want to do today is something not relying on T structures, and it incorporates a lot of representation theory. So I want to start with representations of a group scheme. So if S is a scheme and G over S a group scheme, then what is a representation on a quasi-coherent sheaf over S of G? Over S. That's the following. For all schemes T mapping to S, we have a group homomorphism from G of T, the T-valued points of G, into the automorphisms of the pullback of F to T, which are denoted by Ft. And this assignment should be functorially in T. That's in general a representation. So let's quickly come to the affine case. If S is spec R and G is spec A. So first of all, a group scheme structure on spec A over S is given, yields a Hopf algebra structure, a commutative Hopf algebra structure on A. So A is a commutative Hopf algebra. And the representation amounts, first of all, the sheaf amounts to an A module, an S, an R module. Let's call it M. And the representation corresponds to an A comodular structure on M. Yeah, that's what the representation is. So let's give some examples of group schemes. So for general ring R, we have the general linear group of dimension D over R. And for example, if D is equal to 1, we can easily write down what the representation category is. So I denote by rep G in general the representation category. So in this case, GL1 is GM over R. And that's equivalent to graded R modules, set graded R modules. So you know, representation of GM gives a grading, and that's true in big generality. Could also work over the sphere spectrum, for example. It's also correct. I want to define certain other group schemes which we need in the sequel. So the first group scheme only exists, I define over rational rings. So if R is a commutative Q algebra, I define the orthogonal group. OD of a ring R, the R-valued points, are the matrices in GLD of R with the property that it's orthogonal. So A transpose A is equal to the identity matrix. And what will become important is that this can be also viewed as the fixed points with respect to a certain C2 action on GL D. So this is also equal to GLDR. C2 fixed points, where the C2 action is given. So the non-trivial element tau in C2 acts as follows: A maps to A transpose to the minus 1. So that's the orthogonal version of the orthogonal group. So there are many versions for any non-degenerate symmetric bilinear form. You get an orthogonal group. Here you take the standard form, so to say. If R is in general a commutative algebra, maybe. Okay. I define the symplectic group. So SP 2G of R is given by the matrices A, G, and 2GR with the property that it preserves a symplectic form. So A transpose JA is equal to J, where J is given by the matrix 0, ED minus ED 0. And this also can be described as fixed points of a certain action, namely as GL 2G of R fixed points C2, where tau acts as follows. A is then to minus J, A transpose to the minus 1. J. So J minus J is also the transpose of J and also the inverse of J. So therefore this formula looks like that. And there's a slight enlargement of this group called the general symplectic group. GSP2G of R is given by, so the form is not directly preserved, but up to a scalar. So these are all A in GL2G of R with the property that A transpose J A is equal to lambda J, for lambda some invertible element. So these are the group schemes I want to consider. So I also want to look at derived categories. So in general, I have an algebraic stack X, so up to now non-derived. So it could be BG for some group as above, G. Then the category of quasi-coherent sheaves on X, derived category, can be, for example, defined to be the limit of all derived categories of A, always considered as infinity categories, where we have a general ring, commutative ring A, with the map from spec A to X. So that's one possible definition of this category. And if X, for example, is Noetherian, so some finiteness condition on X, then we also have the bounded category of coherent sheaves on X. So the homology sheaves are coherent and only non-zero infinitely many degrees. So that's a subcategory of DQC of X. Okay. And let's look at some examples of this category. So if K is a field of characteristic 0, quasi-coherent.
Oh,
Yeah. So when we look at an algebraic group over K, like one of these above, and we assume that the identity component is reductive. So this is the case in all the above examples. The only non-connected scheme group is OD, which has two components. Then we can look at this category of applied to BG. so the classifying stack of the group. And then because of this condition, the representation theory is very simple. Every representation decomposes of at least finite dimensional representation into a finite sum of irreducible representations. But every representation is also the inductive limit of all these finite dimensional sub-representations. So in this case, one sees that this is equivalent to really the derived category of the representation category of G. And this in turn is equivalent to just the derived category of the base field, and then a number of copies of it indexed by the isomorphism classes of irreducible representations of G. G. But this last equivalence, it's in general not a tensor equivalence. That's important because, of course, you don't have a tensor product of two irreducible representations need not be irreducible. But for GM, for example, it is the case. Yeah. So in these representation categories we want to study in more detail. So we want to consider symmetric modular functors out of such categories. So in a certain target, and the target will be the category C, which is a K-linear symmetric modular stable presentable category. So a nice co-complete infinity category which is stable, which has also a K-linear structure. Then what can we do? If you have an integer d in n, a natural number, then we can look at the so-called wedge finite objects inside of C. And this I want to be the subgroupoid. The subgroupoid of all x such that, so because it's rational, K is a field of characteristic 0, we can look at symmetric and exterior powers of objects using canonical projectors. And we demand that lambda d of this x is tensor invertible. And lambda d plus 1 x is the 0 object. So a subgroupoid of C of all such x I denote by C wedge d. The exterior, right. It's a summand of the d-fold tensor product of x with itself. Some kind of like the symmetric power, just the exterior power. Yeah. Okay. And then, as I said, we want to study functors into C outside of the representation category, and that's the first theorem I want to state by Ivanari. So the category of symmetric modular left adjoints, maybe K-linear. Symmetric modular left adjoints from this representation category of GLD over K to C. Let's first of all a groupoid, and it is equivalent to C wedge D. And the equivalence is induced by the assignment that a functor f is assigned to f of the standard representation. So the standard representation is a d wedge finite object of the representation category, and it is sent to such an object in C. So that's a correspondence, and yeah, that's a very nice factorization of the representation category. So for example, if d is equal to 1, then the first tensor power is invertible, so X is an object in the Picard groupoid of C. And the second condition here means that the switch isomorphism on X tensor X is equivalent to the identity. So this ensures that the second exterior power of X vanishes. And then we have an induced functor from D of K to the set to C. That corresponds to this X. And so the exterior grading here I denote by set with round brackets. So a set of 1, for example, is then sent to this X. That's how it works in this case. Okay. Yeah. You need right. You need a lot of sure-well duality to prove this theorem, and the symmetric groups appear very frequently in the proof of this guy. Yeah, right.
To relate to the thing you mentioned earlier, that on GM, like where the representation of GM are graded.
Yeah, this is this. D equals 1 is GL. D is then GM, and the representation category is just this category. And a tensor invertible object with this condition is nothing else of a characteristic zero field than as such a symmetric middle functor. Yeah. Okay. Then I want to modify slightly the perspective and incorporate dualities in the picture. So because C is symmetric monoidal, we can look at the full subcategory of rigid objects. Which means, or the rigid subcategory, which means the full subcategory of dualizable objects. Okay. And because every object is then, because if you take twice the duality, you get back the object in this C-rig, you have an induced duality on this category. So it follows that C-rig is a category with duality. And what do I mean by that? It will be an object of the fixed points of the op action on the infinity category of infinity categories. So cat, I denote the infinity category of small infinity categories. And there's a canonical C2 action which sends to its opposite, and taking the homotopy fixed points with respect to this action defines the category of all infinity categories with duality, and you get such an object in here. Okay. Right. So, in fact, the duality can be twisted. So we can get two versions of a duality of a duality on this C-rig. So in fact, two versions. Namely, we can object-wise it's the same duality, but the double dual identification. So if you have an object in C-rig, say Y. And then there's a canonical map to the double dual. And this is used for the standard duality, but we can twist it by -1, by an element which squares to 1. We have the plus -1 dualities, these two versions, on C-rig. The C-wedge D is a full subgroupoid of C-rig. The full subgroupoid, the core groupoid of C-rig. Yeah, because Ivanari's theorem gives you in particular that such X which were in the conditions which were the objects of C wedge D, are in particular dualizable. This gives in particular because the standard representation in here is dualizable. And so we get two versions of dualities on C lambda D, but because it's a groupoid, we get two C2 actions. Two C2 actions on C lambda D, C wedge D. But this space here was the mapping space, mapping into arbitrary target objects in a certain infinity category. So by Ionida and Ioannavis theorem, we get two C2 actions on the category itself. On D rep. Okay. So these are no longer dualities. So it's really a C2 action now. Should not be confused with the dualities. And in which category does this C2 action live? So in the category of commutative algebra objects in K-linear, presentable, stable infinity categories. So I can just write module categories over the category mod K, which is same as D of K. D of K in presentable infinity categories. So this category lives in here, and inside of this category you have this canonical 2C2 actions. This just means, the C2 action is, because this is the mapping space. This is equivalent to the mapping space from drep GLDK to C for arbitrary C in this category. So because you have an action on this mapping space, by Ionida you have an action on this category. So here you have this category. Mapping space in this category is given by this guy, and you have C2 actions here. So it induces C2 actions on the representation category. Yeah. The standard representation is in fact sent to its dual, but it's not a duality, so it's really a C2 action. That says it's a little bit confusing, but you get this. Yeah. And we can identify these C2 actions, so that's the first lemma we have. Namely, plus action is induced by an action on just GLD, and namely the one we have already given, induced by GLDR A maps to A transpose inverse. And for D equals 2G. So the -1 action is also given for odd D, but we don't argue for odd D in this case. We only argue for even D. So it's equal to 2G. Then the -1 action is given by the other action on Gn. GR. A is then to minus J A transpose inverse J. Right, so it comes from a one categorical action. So you have to unwind all the coherences here which are involved here and identify this up to higher coherent actions, so to say, these two actions. You have to do certain steps, but that's possible. Okay. So now, we have the following. Because this category appears on the left of a mapping space, and we have an action, we can take homotopy orbits in the category where all this lives, namely in this category, C2 homotopy orbits. And on mapping spaces, we will arrive at fixed points, because we map out of these orbits then. So what do we get? We get that a symmetrical little k-linear left adjoint from the homotopy orbits into a target category C. This is in one-to-one correspondence with objects in the wedge, in the wedge D finite objects, and homotopy fixed points for the action. Yeah? That's barely by definition of co-limit, so to say. Because you take here the co-limit over BC2, and this transforms to a limit on mapping spaces. Okay. And yeah, the statement that a tensor functor left adjoint k-linear from here to here is in one-to-one correspondence, so there's an equivalence of spaces, so to say, with objects in this space, the homotopy fixed points in this space, of this space. Yeah. And then one of the theorems I want to mention that's joined with Heine is that we can identify these homotopy orbits. So for the +1 action, d k hc2 is just given by the representation category of the fixed points of the group, so to say, d O dk. Yeah, which gives a universal property for this category, hopping out of it. And for the -1 action, we have a similar statement. drep Gucci k hc2 is given by drep sp2g. Okay. Okay. Yeah. And this was our motivating question, if this can be true, because then you get, you can model certain motivi categories by categories of modules of an algebra object in such representation categories. That's what we wanted to do, and this is one of the ingredients we wanted to have. So a sketch proof. Right. We have to work in derived stacks. And the derived affine scheme is an object of the following category. We take simplicial commutative algebras and invert in an infinity category way with the weak equivalences and take of this the opposite. So this I mean by DF, usual category on which you model derived stacks. And on this category we have an étale topology. So by saying on the zero truncation you have an étale map, and then tensoring up to the other homotopy groups you get equivalences or isomorphisms. So we can talk about sheaves on this topology, and these are just derived stacks. So we have the étale topology on EF. Right. And we can compare these derived étale stacks to usual étale stacks on affine schemes. Any étale cover of affines can be considered as an étale cover of D affines, so we have here a natural pullback functor. And this has a left adjoint which is fully faithful. That's a fact from derived stacks. And for example, you take your favorite usual scheme like DLDK and map it into derived stacks. And we denote it by the same symbol. And Now the question is, you have all these C2 actions, and do these C2 actions commute with all the constructions we are doing? So to say, that's the main question. Right. So for example, GLDK C2 fixed points, so which will either be the orthogonal or the symplectic group, is mapped to the corresponding homotopy fixed points in derived stacks. So GLDK HC2. This is true. And the next lemma, I want to maybe also say a little bit about it. So the same works with BGL. So because B is a co-limit, this will be also transferred, so that's easy. But what about the homotopy fixed points? So BGLDK as derived stack, HC2 will be equivalent to BGLDK C2. And here I mean really the scheme fixed points. So how do you see this? So that's this HC2 means you take so to say derived vector bundles on some test affine scheme, and this means that you put a form, a non-degenerate symmetric or antisymmetric bilinear form on it, and so you want to see that this is locally connected in essence to prove this thing. So if you have an arbitrary object here in the homotopy fixed points, over some affine. Yeah.
Mean that here as well, or
yeah, they are the same. I could have written this also, yes.
Put in the source.
There's an H. Yeah, but I can transfer BGL DK via the embedding of the stacks into derived stacks. This I mean by this guy, yeah. I can also take an H here, that's the same. Yeah.
Yeah, the first symbol, upper left-hand symbol here, that was in the category of tall stack, in underived tall stack.
Underived, yes. This was, yes, yes. Yeah, so if you have an object in here, and we also have the standard symmetric or antisymmetric bilinear form, let's call it S, standard form. And we want to see that over an étale cover of A, they become the same. So what we look at is the isomorphism derived scheme between E and S. And this has a map to spec A. And it's seen because that's a torsor under the automorphisms of S, which is either the orthogonal group or the symplectic group. So it's a smooth morphism. And a smooth morphism has étale locally sections. Étale locally sections. So this proves this little lemma. And now we want to argue a little bit for the main result. So we have a comparison map. So we look at the functor QC, which is taking quasi-coherent sheaves in a derived setting, applied to any derived étale stack. So we apply it to BGL DK. And then we form this HC2. So this is exactly what was the left-hand side of our theorem, written differently, because this is an easy stack. This representation category can be described as quasi-coherent sheaves in a derived way, like this. And you have a comparison map to QC applied to the limit inside. But yeah, BGL. HC2. And we want to see it's an equivalence. So this is a commutation of a functor QC from certain stacks to the object, the category where these objects, the quasi-coherent sheaves, live in, opposite. And so the first step is that it commutes with finite limits. So we can take, instead of the limit over Rp infinity, which is BC2, we can take the limit over Rpn, UC BGL dk, and this maps to UC of the limit over Rpn. Okay. But this functor QC, restricted to so-called perfect stacks, was already proven to commute with finite limits. And these stacks in characteristic 0 are perfect stacks. In positive characteristic, in general, you won't have perfect stacks, so then it's more complicated. So a perfect stack is a stack, a geometric stack, so built out of geometric data, such that the category of quasi-coherent sheaves is equivalent to the int completion of the perfect subcategory and has affine diagonal. This means perfect stack. I won't say more to this. So the functor QC from perfect stacks to our target category. So this is C-alch. I'll write it a little bit different now in PL. Mod K under op. So this commutes with finite limits. And this was somehow proved in several papers by, for example, Ben-Zvi, Nadler, Francis, I forgot here, Francis. Or, for example, in a write-up by Gatesbury and also in SAG of Lurie. So we have that these maps are equivalences because Rpn, limit over Rpn is finite. Let's look at some examples what happens for small n. So I denote by x the stack BGL dk. And for example, the limit over S1, which is Rp1 of x. So you have a non-trivial action because it's induced by the C2 action on GLD. So this is equivalent to the pullback of, once the diagonal and once the identity, comma, the action map. So here you don't need higher coherence data because you have the limit over S1. You just get this pullback. And so the next step would be for n equals 2. You get a pullback of the limit. So these are dual cells, so to say. We take the cell attachments of Rpn, getting Rpn plus 1 out of Rpn, and take the duals here, somehow mapping out of it and taking the limits. So we get such diagrams. So here we get the loop stack. So this will be the limit over S1 for the trivial action, which is the free loop stack on X. And here we get the canonical map from X to the loop stack. So here we get the trivial action because you have, so to say, the times 2 action on S1 involved. That's the attaching map for Rp2. And of course, because it's induced by a C2 action, this will be triviality action, this S1. So you get here the loop stack. And n equals 3, for example, you can go on like that, of course. You have here the limit over Rp2, x mapping to x to the S2, and then here x. Pullback of this diagram. So you get all these pullbacks for Rpn finally. And now we want to see that the co-limit, or in both categories, the limit over n commutes with these constructions. So the main point here is that, first of all, you have perfect stacks, so compactly generated stable infinity categories. And second of all, these maps on the bottom here become affine. So you can view everything as sheaves of algebras on your stack X to the limit over RP2 or RP3. That doesn't matter so much. So that's the second step. Write it down, co-limit QC over N, QC applied to the limit over RPN BGL dk is equivalent to QC applied to the limit over RP infinity, which is the homotopy fixed points of the C2 action. GLDK. So we want that this is an equivalence. And the main assertion is that the map X to the Sn is affine for n greater or equal than 2. And then you can test affineness by looking at the zero truncation, and then this Sn doesn't matter so much anymore because you only have higher stuff here which don't matter for the zero truncation, so that's easy to see that they are affine. If you know that you can test it on the zero truncation, and knowing these transition maps are affine shows that then these maps on top for the different ends become affine, and then everything is only encoded in sheaves of algebras over this stack, so to say. So that's the sketch. Okay. But we need a little bit more because the motivic categories look a little bit differently. We don't have really an object with antisymmetric duality, but a pairing into not the tensor unit, but a tensor invertible object. So therefore, we need the following: that the category drep G sp2G. Okay. So we need also a universal property for this category. The mapping out of it in a k-linear left adjoint way, symmetric monoidal, into some target category C. This corresponds to now the following data: D-wedge finite object and tensor invertible object. So this trivial switch map. So that's an object of C wedge 1 and antisymmetric pairing from X tensor X to K. Antisymmetric on the channel. Okay. So that's the universal property of this category. I want so only one remark about the proof. You want to use the universal property of the symplectic group. So what you do, you adjoin to C the square root of K of this object. And then you can twist X down with the square root of K or minus the square root of K to get the tensor unit on the right-hand side here. And this adjoining, the square root is given by push out in the corresponding category of d of k to the set, to d of k to the set. Here you induce it by the multiplication by 2 map on set. So this gives you the square root, and here you have the canonical map corresponding to this object k here. This one here. To C. So this you use for the proof of this theorem. Exactly. So these are the purely representation theoretic ingredients. And now I want to get to applications to motifs. Yeah. First, to give you some flavor of what theorems we are interested in. So, if S is a scheme, then we can look, there is a triangulated category of motives over S, denoted by dm of S. You can define it as the module category over some motivic Eilenberg-MacLane spectrum MC in the P1 stable motivic category of S, SH of S. So now I look at easy objects in this category, namely the Tate objects. Therefore, I only look at representations of GM, which is D up to the set, if the coefficients are the integers. And there's a natural tensor functor to dm of S, which sends object in outer degree n to the Tate object of twist n. So these are certain natural objects here in this category, defined by tensor powers of projective spaces. And this functor will have a right adjoint R. And we can define the so-called motivic E infinity algebra A to be R of the tensor unit on the right-hand side. So that's a certain graded E infinity algebra over the integers. And an easy consequence of some categorical reasoning, because all these are tensor invertible, these objects, is that the module category over A on the left-hand side here is equivalent to a full subcategory of this right-hand side, namely the category of mixed Tate motives, triangulated mixed Tate motives over S. R is the right adjoint to this natural functor here. Let's call it L. This here. That's R, L is symmetric monoidal, so R is lexsymmetric monoidal. So it preserves commutative algebra objects. This lives in C arch. Yeah, up to the set. Here you need S quasi-compact quasi-separator to be compactly generated on the right-hand side. Right. And so that's kind of not so deep. But now we want to generalize it a little bit. First of all, I want to give you some flavor that you can incorporate finite étale schemes over S on the right-hand side. And this, here we use the work of Bachmann-Euler. Namely, for such an S here, one can define the so-called étale fundamental groupoid, pi1 head of S, fundamental groupoid. If S is connected, this would be B of the étale fundamental group at a given base point. In general, it's a pro-finite groupoid, so an object in the pro category of finite groupoids. And so this example which I give at the moment is a little bit independent of the rest, but it gives you some flavor of what the ideas are. So you can look at the genuine, I call this G, and you can look at the genuine equivariant G equivariant category spectra. So if G would be BG for G of finite group, this is usual genuine G equivariant stable homotopy category. And Bachmann-Euler constructed a natural map to SH of S, which looks as follows. If you have a finite G set here, or the suspension spectrum in this category of such a thing, X, then a finite G set corresponds to a finite étale cover of S, and you get the corresponding suspension spectrum on the right-hand side. The finite étale cover of S. You have this natural left adjoint here, and
the set just point to S.
Yes, a point tends to S. And for example, if you have a Galois group, then finite quotients of the full étale fundamental group correspond to finite étale maps, and this is sent to here. Yeah. So for example, if S would be spec R, the reals, then this G would be just BC2, and the orbit C2 would be sent to, or the free C2 set C2 would be sent to the complex numbers. Suspension for of the complex set. Yeah. Okay. So now we can prolong it to the M of S. But here we have this other functor from D up to the set, so we can combine them into a functor SPG tensor D up to the set into dm. So the target will be mixed R-tailed motifs to dmat of S. That's just the full subcategory here on the right-hand side generated by the image of these functors here. And right. So we can play the same game. We can apply the right adjoint here. Then we can model the right-hand side by algebras over R of 1. So that's the same story, but modeling all R-tailed motifs, so to say. And but what is more interesting, maybe in this context here, for our group, is that we can upgrade this algebra. That's first of all just an E-infinity algebra on this left-hand side, but we can upgrade it to a graded normed algebra. So an N-infinity algebra in a graded sense. For all norms, multiplicative norms, so to say, which are possible here. So this is work of my PhD student Ushogov. Yeah. So this can be done. So that's an example of a nice normed algebra. Normed in the sense of Bachmann-Euler. And now we can compare it to all other versions, all other flavors. So it's just an N-infinity algebra. Okay. And now in the end, I want to come back to what I started with, namely how the representation categories come into the picture. So this works not for DM, but for étale motifs, first of all. So this is a category which I want to define quickly. The étale motifs over S. That's the P1 stabilization. P1 stabilization of the A1 localization of a certain derived category of sheaths, namely on smooth set schemes with respect to the étale, S schemes with respect to the étale topology with integer coefficients. And yeah. So that's just the usual stable infinity category, derived category of a certain sheaf category. You can A1 localize it. That's equivalent to looking at A1 local objects in this category. And then you have an n functor given by tensoring with P1, and you stabilize with respect to this one. And so that's Ayub's category of étale motifs. So now we want an object in this category, at least after rationalization, which lives in this, which is wedge definite. To apply our representation theorem, first of all the Ivanaris theorem, and then in a second step our theorems. And this is given by motifs of abelian schemes. So the theorem is the following: if S is Noetherian, finite dimensional and excellent. So these are conditions that a certain theorem of Ayub is satisfied. And A over S is a principally polarized. So this means that a certain duality, that the dual abelian scheme, which parameterizes certain line bundles on A, is equivalent in a natural symmetric way to A itself, isomorphic. So a principally polarized abelian scheme. Then the theorem is combining a rational result and also integral finite coefficient results, that there exists no longer very canonical, but there exists a symmetric monoidal left adjoint from a certain representation category. And this will be no longer the quasi-coherent sheaves on a certain classifying stack, but the incoherent sheaves. So the int category of the bounded of the coherent sheaves on the classifying stack B, GSP to G over the integers. So this is no longer over the rationals, but over the integers. So there's a map functor into this category DRES, which sends the standard representation of on a 2G rank set module of GSP to GSP to G to the one motive, so-called one motive of A, which is, so to say, the H1 of A, so the first homology model. And as you know, so topologically, this would be a torus of dimension 2G. And the first homology group carries an antisymmetric non-degenerate bilinear pairing. And this corresponds to the fact that we can work here with this group, so to say. And this also is true in the motivic setting. Yeah. So that's the second main theorem, that we get such a left adjoint. And you have to work first rationally and use our theorem about the universal property of the representation category. And then you have to do other things with finite coefficients and glue all the functors you get along an arithmetic square, so to say. Right. You have a pairing here, a symplectic pairing to C1. And that's the reason why we need the GSP thing here. Ah. Yeah, exactly. Yeah. Okay. And maybe possible applications. So in this representation category, you can form a lot of nice objects, of course. You just write down a finitely generated abelian group, say H, with the representation of GSP2G on it. An algebraic representation, of course. And then you get a motive. So for example, you can take symmetric or exterior powers of H1 of A living in this category without any homotopy stuff. So on the right-hand side, you cannot do this in this category DA8 because you don't have a natural T structure and such things. But here you have it, and you can perform certain one-categorical manipulations and end up with maybe new motives which you can construct in this way. That's the idea behind it. Yeah, that's it, what I wanted to talk about. Thank you very much.
Questions? So when you take the right adjoint, you get an algebra that
Yes.
tells you what the A motives are, so the category
Yes.
is represented by A. Is that
Yes, yes. Probably a little bit bigger because you get more representations in this category, but more than generated by the standard representation. I mean, the standard representation here goes to H1 of A, and you can look at the right-hand side just generated by tensor products, duals, and all colimits and all shifts by this H1 of A. But you probably get a little bit bigger category because such representations here are maybe not, I don't know it, but they might not be generated by the standard representation. These integral representation. Or rationally, of course, it's clear. Rationally, it's the same, but integrally, I don't know. Yeah. But you can do it, yes. You can apply the right adjoint here. Yes.
So this gives you like for an elliptic curve.
Yeah.
It gives you the description of elliptic motives.
Exactly. The usual. I should have mentioned some names here. I forgot. So, for example, your student Chin Kao, for example, did something on elliptic motives. Yes, yes, yes.
In order, I mean, there's this, you still need, he was trying to get some abelian category and then you needed additional.
You need the Bellizzi-Sully vanishing conjecture, and plus other stuff. Okay. Yes, 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 yes. Right. Oh.
Right. Well, thank you.
Thank you.